Now let's see how transistor works as an amplifier. We are taking the common emitter case, common emitter configuration, and in NPN configuration, right? This is the transistor we'll be using to work it as an amplifier. See, this is our base region, collector, emitter. Since this is an NPN, so it will be like this, right? We already know that emitter base, this is emitter, this is base, and emitter base region is supposed to be in forward bias state. So positive to positive, negative to negative, variable voltage, and this is now in forward bias state. Now what next? This region, the collector and emitter region. First of all, connect it with a load resistance RL. This is variable load resistor RL, and then a voltage which drives the collector emitter circuit. Let's call it VCC. Voltage between just VCC, okay? I'll be using VCE for something else. I'll tell you again. This is the other part of the circuit, and this is where we are deriving our output from. That means this, from this point to this point, is our output. Now where is input? How does an amplifier work? What exactly is an amplifier? Amplifier is a device which increases the amplitude of the input graph or input AC, right? So where is our input AC? Okay, one thing I missed, the input resistor RB. In NCRTs you will find these kind of diagrams. You won't need to put up any circle here because just this much will do, alright. Students are usually advised to put up this circle just to show that this particular part is a transistor, but even without this works perfectly fine. In NCRTs, the input voltage is given by this, a capacitor accompanied with the input voltage. This is the AC which has to be amplified. That is what this amplifier circuit is about. But it is even easier to understand this whole thing when I draw the circuit. See where I am putting this input, the AC which is to be amplified. This was our forward voltage for emitter base part. This is where I am putting my input cycles which is to be amplified. This will make your understanding more clear. Let's first write all the directions of current. This is how current is flowing in the part, and further this will be the direction of emitter. No, not this arrow, because this is what? This is an emitter part. There won't be arrow inside here. This will be the direction of flow of current. Apply Kirchoff. You remember Kirchoff's law? Let's apply Kirchoff's law at this point. This is connected to emitter current. This is IC. Emitter current IC. This is going to base current IB. This is going to collector current, which is IC, right? This was IE, emitter current. This is E. IE. Now at this junction, according to, where should I write? According to Kirchoff's current law or junction rule, IE is equal to IB plus IC, right? Emitter current is equal to base current plus collector current. Even you have to keep this point in mind that collector current was 95% of what emitter current was. Number 2, this is our collector, this is our base, this is our emitter. So if I want to write, or if I want to apply Kirchoff's law, Kirchoff's voltage law, loop rule between point collector to emitter in this part, in this circuit, from collector to emitter, what would my equation look like? My equation would look like, this is what I am writing, voltage between collector to emitter. I am going in this direction. So first of all, I am getting the product of collector current and resistance ICRL. ICRL with a negative sign. Why? Because I am going in this direction, current is going in upward direction, so minus ICRL, and plus I have met the positive terminal of the battery, so plus VCC. This is the equation, right? But this part VCE, that is the voltage between collector and emitter, is actually our this voltage between this point to this point, which is actually our output voltage. So I am writing it like with V naught. This part is V naught. V naught is VCC minus ICRL, right? I want this space empty, so I am writing it here. V naught is equal to this is VCC minus ICRL, right? This is our second equation. Now, how does it work as an amplifier? See, we are clear with these two equations. During positive half cycle, suppose this is our input graph, input cycle. During positive half cycle, it's like this. So current is flowing in the same direction as it was supported by the forward bias voltage of emitter base voltage. So this current is actually getting increased due to the supportive voltage. What will happen? This will going to support the forward biasing of emitter base voltage. See, this is already an emitter bias voltage which is doing the what? This is doing the forward biasing of emitter base junction. Emitter base junction. Now this emitter base voltage is getting increased or getting supported due to the positive half cycle. So what will happen? More forward biasing, that means more emitter current. Emitter current increases, that means it will ultimately lead to collector current to increase very high. If this value is increased, this whole part becomes very large, and due to this output becomes very small, more negative. So very small means more negative. So due to this positive half cycle, we will get a very large negative half cycle. When input circuit is in negative half cycle, the forward biasing is getting opposed. It is not getting reverse bias. The forward biasing is getting opposed, due to which emitter current will decrease. Emitter current will decrease, will lead to collector current to decrease very high, and this part IC into RL becomes very low, due to which output becomes more positive because this value was already very high. So this becomes more positive. So they are in 180 degree phase difference, input voltage and output voltage. This is how a NPN transistor works like a amplifier.